Chapter 3 or Module 3, pitot-static system, going in depth or in detail into that system, although we kind of covered it before. So, what are the principles of air pressure measurement? Because, as we mentioned, ASI, the VSI, and the altimeter, the three of them depend on the measurement of air pressure, okay, and the difference between the static air pressure and the dynamic air pressure. Also, dynamic being 1/2 rho v square, the moving air, the pressure of the moving air, and the static external air, okay, like the pressure of the air from the outside. So the difference, yeah, basically, exactly. The difference between the dynamic air and the static air is what gives us the airspeed, the altitude, and the VSI, vertical speed indicator value, or the climb or descent rate. Okay, so the pitot-static system is a fundamental aircraft system. It is very critical. You cannot go without it. This is how fundamental it is. It is used to measure air pressure and convert it into meaningful flight information. It operates by sensing pressure differences, as we mentioned before, caused by aircraft motion through the atmosphere and changes in altitude. The air pressure in the atmosphere decreases with the increase in altitude, as we also explained prior to this slide, due to the reduction of what? Of the density of the air. So as you go upward, the air density decreases. This is due to the factor of gravity. So as close as the air is to the ground, it would be more dense. Why? Because it's closer to the gravity, to the center of the gravity of the entire, globe. Meanwhile, and due to the rotation of the Earth, the air would be moving like it would be more condensed and concentrated on low altitudes, and then due to the rotation, which generates a centrifugal force, it would be thrown, okay, in lower densities around, it would be scattered around the globe. So as you go up in the altitude, you would have lighter and lighter densities of air, okay, lighter concentration of the air molecules as you go up. Meanwhile, as you go down into altitude and as you close up to the ground surface, like the level 0, altitude 0 of the globe, anywhere in the world, you would have the higher density of air, okay? It would be more condensed due to the weight factor, okay? So it would be weightier and more condensed close to the ground, okay? Again, you have two forces in action here. You have the gravity, which pulls the air downwards, and you have the centrifugal force, which is a force generated by the motion of by the rotation motion of the globe, of the Earth, which pulls everything outward. So these two will make the air molecules more dense, okay, closer to the Earth's surface, and when you go outwardly, they will start to scatter more and more. All right. Now, so air pressure in the atmosphere decreases with increasing altitude due to reduction in air density. Aircraft instruments exploit this predictable variation to determine altitude, airspeed, and vertical speed. The pitot-static system consists of two primary pressure sources. You have the total pressure, which is static plus dynamic pressure, by the way, and the static pressure, which is the pressure of the closed air within the static source, okay? This is where you have wrapped and sealed the air when the aircraft was still on the ground, on the runway, before climbing, okay, before starting the journey. So these pressures are transmitted through tubing, which is the pitot tube here, to flight instruments where mechanical or electronic mechanisms convert pressure values into readable indications, which are airspeed, vertical speed, and altimeter. Okay, so as we see here in the pitot tube, you have the ram air entering through that tube, okay, a baffle plate, like the eardrum somewhat. Okay, pitot tube. It's conducted inwardly. You have a heater. By the way, why is the heater, which is in both locations here, heater at 100 watts and at 35 watts, it is necessary in order to prevent icing conditions. Otherwise, that would lead, the icing would lead to the blockage of the tube. So the air would be constricted, which will lead into unreadable data or erroneous data, okay, erroneous airspeed measurements, which would affect the three of these instruments, especially the ASI. Okay, the airspeed would be faulty, which happens once on an aircraft, okay, where one of the pitot tubes were blocked, which drawn down the airplane. It crashed the airplane due to that factor. So now, speaking of which, how does the blockage of the pitot tube affect the airspeed indicator? You see, when you have a blockage of icing in this case, any type of blockage is bad. And this is why, by the way, you have the heater in order to melt the ice to prevent any blockage of the pitot tube. But when you have icing, okay, during takeoff, the airspeed would be very slow, appearing to be very slow, okay? Why? Because the density of the air on ground level would prevent the air from flowing in an efficient way within the tube, depending on how much is the rate of the blockage. Now, the funny thing is that when the aircraft becomes airborne and as the density of the air goes down, okay, this small cavity, which has not been blocked, given that the ice has not blocked the pitot tube at 100%, but this remaining cavity within the tube that is still allowing air to go through it, okay, when you have low density air, it would flow through that cavity at a high speed. That will actually show to you on the display an overspeeding, okay, speed value, an airspeed value way above the actual real speed value, airspeed value. So this is how faulty the indicator would be. So you would be getting an overspeed reading, meanwhile the aircraft is stalling. And this has appeared on that flight, I don't remember which one, a conflicting reading. So you had an airspeed, an overspeeding indication, okay, and then the stick shaker. Why? Because the actual real airspeed was much lower than the one indicated, and the one indicated was too high, okay, was actually overboard due to the fact that the pitot tube that was blocked led to a wrong measurement, a very wrong measurement, giving a very inaccurate and overly high airspeed. All right, now let's start talking about the static pressure. So what is the static pressure? It is the ambient atmospheric pressure surrounding the aircraft, sensed through static ports mounted flush with the aircraft fuselage, okay, to minimize airflow disturbance. Now, static pressure is used directly by the altimeter and vertical speed indicator, and indirectly by the airspeed indicator. So static pressure is used by the altimeter to measure the difference between the ambient pressure and the locked pressure of the air that is sealed within the diaphragms, okay, the diaphragm, this compartment. So by measuring the difference, we can get the altimeter, and the speed of change of this measurement, okay, the speed of change of the rate or the difference between actual pressure on the outside of this diaphragm and that on the inside, the rate of change would give you the VSI or vertical speed indicator. And finally, you have the ASI, which works based on the dynamic pressure of the air flowing that's pushing against a diaphragm. This push would give you the dynamic pressure, which is Q equal 1/2 rho V square, from which, and given that we know the density, okay, the exact value of the density, you can get the velocity of the aircraft, which is the velocity of air or the airspeed, okay? The same thing, using this very same formula. Pitot pressure. So, pitot pressure is the pressure measured at the pitot tube opening facing the airflow. It represents the total pressure, which is the static pressure plus the dynamic or ram pressure, the pressure of the air entering. Dynamic pressure is not measured against its surface, is the pressure of the airflow or the air flowing through the pitot tube, which is again 1/2 rho V squared. So the pitot pressure is the sum of both static pressure plus the dynamic or ram pressure created by the aircraft's forward motion through the air. Okay? Total and dynamic pressure. According to Bernoulli's equation for fluid motion, for the motion of fluids, and it's not only aerodynamics. Okay? Aerodynamics is one application, but it is applicable for different types of fluids, such as water, such as different other types of liquids, different other types of gases. So, based on Bernoulli's equation, the total pressure, PT, is equal to static pressure, which is force divided by area, where the force is being applied, plus dynamic pressure, or Q, which is 1/2 rho V squared. Okay? So, to give you an example, imagine the air around a wing. Okay, so the total pressure would be equal to static pressure, which is the force per unit area against the wing, plus the dynamic pressure or the air flowing around the wing, which would be dependent on the velocity of the air and the density, 1/2 rho V squared. So Q, or dynamic pressure, is equal to 1/2 rho, which is the air density, times V squared, which is the true airspeed of the air. So PT, or total pitot pressure, is equal to static pressure plus dynamic pressure, Q, which is the dynamic pressure, is 1/2 rho air density times V squared, true airspeed. This pressure difference forms the basis for airspeed measurement. Again, as we mentioned before, the difference between the ram pressure and the static pressure is what gives us the airspeed and other indicators. The ASI, or Airspeed Indicator. So how does it work? The Airspeed Indicator measures the difference between pitot pressure, which is the pressure of the incoming ram air, and the static pressure. Okay? Now, and we mentioned before that internally a diaphragm connected to the pitot pressure expands or contracts relative to the surrounding static pressure. Okay? Now, the indicated IAS, okay, indicated airspeed, is proportional to the square root of the dynamic pressure, correct? So this is basically V equal square root of 2 times PT minus PS divided by rho, correct? So if you basically place, if I want to resolve it, this is the application to the same equation that you've seen it before. So we have P total equal PS plus Q, which is 1/2 rho V squared. So you have PT minus PS times 2, okay, equal rho V squared, correct? So V is equal to the square root of 2 static total pressure minus static pressure, 2 PT minus PS divided by rho. This is how you get the velocity. In practice, the ASI is calibrated assuming standard atmospheric conditions, which is done on ground level, as we mentioned before. So it is calibrated based on the air pressure at the ground level, which introduces errors at non-standard temperatures or altitudes. So when the temperatures change or specific altitudes change, it would produce some errors. You won't have accurate results. Why? Because you're depending on, or the dynamic pressure from which you get the velocity, the airspeed, is dependent on the density. And the density, when it changes everything. It changes the dynamic pressure, but it also will change the velocity or the airspeed value being measured within the instrument. That's why you would have an error margin that should be accounted for. And this is why we need to recalibrate the instrument based on these varying conditions. Now, types of airspeed. You have indicated airspeed, which is the value read on the instrument, calibrated airspeed or CAS after calibration, okay, after readjustment, true airspeed, the TAS, okay, which is the real airspeed, the true value, which is rarely the exact value, the 100% value, exact value measured by the instrument, and the ground speed, which depends on the GPS system, okay, and other things. You have also a ground measurement based on a transmitter and receiver that transmits to the ground a signal, then this signal is received back, okay? So by measuring the time it took for the signal to go down then up, okay, and by comparing it with the altitude, you would get what? The distance traveled, okay? Now, before that, so the true airspeed can be approximated from the indicated airspeed using the TAS, or true airspeed is approximately equal to the indicated airspeed square root of rho 0, which is the sea level standard density, around 1.02 kilograms per meter cube at sea level. That would be the nominal air density at sea level, okay, at specific temperatures, divided by rho, which is the actual density at that specific level, okay, the actual density or the current density at that specific height. Now, going back to how do we measure the speed based on, the ground speed instrument, okay? So based on the transmission to the ground method. So you'd have the airplane here, okay? It would send a signal, then it would receive back the signal, correct? So how long did it take the signal to go up and down? That would give us this full distance traveled, and you would have what? The height here, okay? The altitude, which we can get from the altitude. So what we need is the distance from here to here, okay? That distance. So let's say, okay, I'm getting one section here. Okay, so you would have, so how long did it take? So you have this distance over here, let's say, okay. Yeah, so d square, we know that d square is equal to h square plus, let's say the travel distance is r, plus r square. And this is how you can get r. R would be the square root of a square plus h square, okay? Altimeter, okay. The altimeter measures aircraft altitude by sensing static pressure, correct? It contains one or more sealed aneroid capsules that expand as pressure decreases. Why? Because the difference between the internal pressure, which becomes higher than the external pressure as you climb, as you increase in altitude, as the aircraft goes up in altitude. So the difference between the internal pressure within the diaphragm and the external pressure increases, which makes the diaphragm, okay, or causes the diaphragm to expand. Why? Because the pressure on the inside has become greater than that on the outside. So it dilates. And as it dilates, it rotates you have like a gear. It rotates this handle that turns the gears, which is in its turn connected to the needle that measures the altitude. Okay, that goes for the mechanical instrument. Okay, mechanical type of instrument. So the relationship between pressure and altitude in the international standard atmosphere ISA can be approximated by. Okay, so H or altitude is equal to T0, which is the temperature at sea level, divided by L, which is the temperature lapse rate. Okay, the temperature excursion. Okay, how much the L is has a lapse. Okay, the different temperature being measured, multiplied by 1 minus PS over P0. PS is the static pressure at that altitude divided by P0, which is the sea level pressure, okay, to the power of R L divided by G. G is the gravitational acceleration or gravity. Okay, R is the specific gas constant of the air and multiplied by L, which is the temperature lapse rate again. So now altimeters require barometric setting adjustments to account for local pressure variations, commonly set as QNH or QFE or standard pressure, which is 1013.25 HPA. Okay, so they need readjustment in order to keep them producing accurate results, accurate measurements. I feel the need to reiterate on this formula because it might look a little bit ambiguous or hard to understand. I felt that we have passed over it a little bit too quickly. So again, this is how the altimeter would display for us the current altitude of the aircraft based on these parameters. These are the parameters, or at least some of them, that I've seen or perceived as a little bit complex to understand. Okay, little bit ambiguous. So H, which is the altitude of the aircraft, is given by T0 or sea level temperature divided by L. L is the temperature lapse rate, or in other words, how much is the temperature changing per unit altitude. In other words, to make it simpler, how much degrees is it changing per kilometer. So let's say you have a change of 0.005 degrees Celsius per kilometer or degree Kelvin per kilometer. I'm not sure about the international system unit being used here. That would be the lapse. Okay, so it would be 0.005 and you place it within this equation. Okay, multiplied by 1 minus PS over P0. PS is the static pressure within the compartment, within the diaphragm, the current static pressure, okay, which will expand. Okay, it would change due to dilation because of the external air having a lower pressure than the one that is locked or sealed within the diaphragm, okay, that has been sealed from the ground level. So PS is the current static pressure divided by P0, which is the pressure at sea level, okay, to the power of RL divided by G. R is the gas constant, we know it, okay, each gas has a constant, multiplied by L, which is the temperature lapse rate, divided by G, which is the gravity or gravitational acceleration. VSI or vertical speed indicator. Now, as we probably have already mentioned, that the VSI or vertical speed indicator measures the rate of change of static pressure, not the difference between the static pressure and the sea level pressure, okay, the actual PS and P0 at sea level, but rather the rate of change or the speed of change, okay, providing the aircraft's rate of climb or descent. So the VSI operates on the principle VSI value is proportional to the derivative or the rate of change, in other words, of the static pressure, okay, of the static pressure in respect of time. So it's delta PS divided by delta T, or P final during a span of time, P final minus P initial, divided by T final minus T initial, okay? Which again, it can also be looked at, because it is the derivative of the pressure in respect of time, or in other words, less technically, it is the speed of change of pressure in respect of time, the static pressure mainly. Now, so you have a calibrated leak which allows the pressure changes to lag within the instrument in order to be able to measure, okay, the difference between the actual static pressure or the static pressure at this moment and the former static pressure. So for us to have a former static pressure, you have the need for a lag, like a little delay between the current pressure, okay, and the former pressure. So the current pressure of the air sipping outside from this bleeder, this calibrated leak, okay, the current pressure at this moment, and yeah, the former pressure from moments ago. This is how you measure the change rate, okay, of the pressure, from which you can get the VSI. Now, by the way, how it works is that you have, let's say, if you're climbing, during the climb, the diaphragm would dilate, okay? So this dilation, this expansion would make the pressure of the air at that moment less than the static pressure that was formerly on the inside. So this motion, this lagging motion, is what will move the needle, okay? And it will move it upward to display or indicate a positive rate, okay? So a reduction of air pressure would cause a positive rate, or the needle moving upward positively, indicating that the aircraft is climbing. And the opposite, you know, is you can reciprocate for the opposite, meaning that during the descent, what will happen is that the diaphragm would collapse under an increasing pressure, okay, which will cause also the needle to move, but this time it will move downward, okay, due to increased pressure, it will move downward, indicating a descent, okay. And how much it has moved, it will indicate a descent rate, as long as this pressure is decreasing. Now, once the change of the pressure had stopped, the needle would stabilize again, or it would be leveled again to zero, okay. That would display or reference a leveled flight. Now, this leak is important for the needle movement, okay. This lag created by the calibrated leak is the reference, okay, is the action by which it is allowed, like the instrument is allowed to have pressure changes, okay, that will actually affect the needle to rotate one way or another, causing the pressure differential across a diaphragm that drives the needle to indicate whether positive climb or negative climb. However, there's a trade-off. There's a compromise here. Due to this design, the VSI exhibits a time delay, typically 6-9 seconds, which is a delay between the actual altitude, okay, the actual vertical speed that the aircraft is experiencing versus the displayed or indicated vertical airspeed. So you would have a difference between the actual vertical speed during the climb or descent and versus the indicated one, okay. So the indicated VSI value would need or require a little bit more time, some few seconds, up to 6 to 9 seconds, to be updated to the actual real value. That's the problem, okay, between a change in vertical speed and indication. So there's a trade-off, but this is the problem, that the VSI actually works using the bleeder, using the calibrated leak. That despite the fact that it induces a typical delay of 6 to 9 seconds. This is how it works in order to display the VSI value on, the instrument or on the indicator via the needle motion. Now, common errors and failures. Okay, let's talk about that. So, at first, we have pressure and instrument errors. Okay, for example, pitot-static instruments are subject to several error types. For instance, you have position error due to airflow distortion. You have miscalibration also on the ground level of the pitot-static system. Instrument error from mechanical imperfections, because as we know, you have the diaphragm motion is what we rely upon to measure different things. These different parameters such as VSI altimeter and the airspeed. So a mechanical fault within the instrument can lead to a misreading. Okay, it can break in flight at times. Nobody knows. Okay, so density error caused by non-standard temperature, also another factor. So a difference of density or density error due to a temperature that's not common. Okay, for instance, you have a phenomena above the desert. Usually you would get a hot air above a cold air which would be close to the ground. Okay, so an inversion may occur. Usually you have the cold air above, okay, and a hot air below. So this is what you're getting. You're getting a different false measurement. Lag during rapid altitude changes. So this lag due to sudden fluctuations of pressure, okay, would cause a misreading in altitudes also. Now, another factor is the blockages and leaks. So blockages in the pitot tube or static ports can result from ice, insects, or debris. We had that problem happen multiple times. Like actually, there was an incident in which the pitot tube, I referred to it in former slides, it was blocked due to an insect that formed its own like a fabric, like a housing for itself within the pitot tube, which led to the aircraft going down due to the misreading of the airspeed. So this blocked pitot tube causes the ASI to act as an altimeter during climbs or descents. Okay, so a blocked static port affects all pitot-static instruments. Leaks in the system lead to sluggish or incorrect indications and can severely degrade instrument accuracy. So leak within the diaphragm, for example, not the acceptable leak within the VSI, but if there's problems like that, these leaks would cause us to have a wrong difference between the static pressure, okay, the actual current static pressure, and the sea level pressure. Okay, so it would lead to wrong measurements, correct? And the system would be acting or giving sluggish values or incorrect indications. Okay, can severely degrade instrument accuracy again. Icing effects. One of the most serious problems that can occur, and it can seriously and it will seriously affect readings in instruments, not only, by the way, the instruments, it affects the entire airplane, especially introducing drag on the wings, and it can lead to stall by reducing the lift and increasing the drag factor on the wings, okay, deteriorating the wing characteristics, okay, and converting a laminar flow into turbulent flow. This will kill the lift force that is supposed to be pushing the plane upward, okay, and keeping it in the air. So icing effects. The icing is the one of the most hazardous pitot-static failures. Ice accumulation can block pressure sources, leading to false airspeed and altitude readings. We've already covered that. Pitot heating systems should be introduced, and they are installed to prevent ice formation both on the front and the back, and ensure reliable operation of the instrument, the pitot-static system altogether, even in icing conditions, which is very important. Operational implications. Pilots must cross-check pitot-static instruments and recognize failure symptoms if the readings don't make any sense. Okay, for instance, they need to check these values promptly, and understanding system principles allows correct diagnosis and troubleshooting and safe continuation of the flight even under abnormal conditions by looking at the indicators, because since you have a redundancy, you can look at the indicators that seem to be working properly and normally, and these would be the indicators or the instruments that are the backup that you would rely on in order to continue the flight instead of going or referring to the main system that has a defect. Let's say one of the pitot-static systems or the pitot tubes to the left or to the right has been blocked. Okay, you should isolate the problem, and by the way, you should also deactivate the autopilot, especially if it's getting its reading from the faulty pitot tube. Otherwise, it can bring down the airplane. So you would need to rely on the other instrument and then go back. It's preferably go back to the runway, to the airport, in order to fix the problem.